Okay, sorry for the lateness. So this course is called the varied polarimetry, and so we would want to introduce just a brief introduce about the operation of the weather radars with the and its interactions with the atmospheric components. So we have just I think 16 hours. So we're gonna divide it each to be 5 1/3 lectures. So as two is for the antennas, because for the interaction for the detection or monitoring of the weather conditions, the efficiency and the capability and the accuracy of the detection is mainly determined by the operating wavelengths and also by the antennas. So this is gonna take us around 2 lectures, okay, and including this time. And another 2 lectures is for the microwave interaction with the atmospheric constituents. So we're gonna introduce the interaction with the different kinds of weathers and the atmospheric particles, and the gaseous particles also. One is for the weather radar operation, and is the operational mechanisms. And the last 1/3 is just for the weather radar calibration. So collaboration is very important. I think, as you know, that we have the collaborations with the meteorological community of China, and we have a collaborational lab with them also. So we're gonna have several projects on the radar collaboration, and especially they have their collaborational center at the Changsha and Hunan province. So this is going to be an important point for the weather radar system now, as because the collaboration helps to improve its accuracy for the detections, and also improve the accuracy for the forecast weathers. So for the final score, I think they're going to be composed by 2 parts. And the first part is the homework, and a short homework shows it's going to take 30%. And at the final, there's going to be a final report. So I'm going to assign several topics for that, and I hope you can choose one of that for your final examination, maybe. Yeah. Okay. So now I think the first we're gonna start is for the antennas. I think most of you are familiar. Most of you are familiar with the antennas. So it performs as transform from the transmission line and launch the electromagnetic waves to the first base, right? So at the so for example, let's take a Horn antenna as an example, and for a Horn antenna, looks just a shape, okay? So this is a Horn antenna. That's very simple, right? And that's the most commonly used for our investigations. And we have many kinds of antennas, especially, for example, the cascading antennas, all right? And also for the dipole antennas, and the pattern antennas, and the antenna arrays, all right? So we just take the Horn as an example. So if you have used Horn antennas for the for your research works, and you're going to say that at the other side, so this is aperture, right? And on the other side, it connects to the generator. So the generator here. And the generator generates the energy, and it propagates inside of it. And then it's going to be converted to the electromagnetic waves. Right? Inside of the antennas. So when it goes outside of the aperture, they're going to be the actual electromagnetic waves, right? So this one. This one, all right? And for a long distance, it becomes, so previously the launch of the electromagnetic waves launched out from the aperture, it's going to be spherical, right? Actually, especially for a point source. So after that, it's going to become, over a long distance, or the far field, or the far zone, it becomes plane wave, all right? So this is what we already used for the analysis of the electromagnetic waves when it propagates, and we take it as the condition of the far field region, because its phase form can be regarded as a flat plane, all right? So this is for the antenna at the generator side, and so at this side, this is still energy here generated from the generator, and we take this side as the transmission line here. Because sometimes, mostly it can be a waveguide. Actually, if you look at from the front of the antennas, from its aperture, look inside of the whole antennas, you're going to see there is a waveguide, right? So it has a very tiny aperture, and after that, then this side is the transmission region here. So at the transmission region here, there is already, because it interacts with the surfaces of the Horn, and they are going to be the conduction current flows on the surface of the antennas, right? And so it will interact with the surface, and after that, it's going to convert it to be the electromagnetic waves and after into the free space. So an antenna is usually regarded as a transducer. Is regarded as a transducer that converts a guided wave, right, from the waveguide propagating on a transmission line into an unbounded medium. So here I take it as the unbounded medium instead of the free space, because the electromagnetic waves may not just propagate in free space, right? They can be in other mediums such as the sea, all right, ocean, or under the surface, ocean water, for example, all right, and under the ground. So just it is propagating unbounded medium, all right? That means it is a wire instead of the wire. So this is for the here we just shows the propagation, the condition for the generator side. Okay, and on the receiver side, we still have such an antenna, but now it's some things different. So at this side, this is the receiver, right? And this is, but at closing to the aperture of the antenna, the electromagnetic waves are plane waves, all right? Because it propagates from far field to the to this side, all right? So it can be regarded as a flat plane, and then it is intersected by the antenna and enters the aperture, all right? And this is the transmission region, and then into the transmission line, all right, to the receiver. Am I correct? So there is one parameter that we really need to consider as the antenna efficiency, right? For each antennas, the generator generates the energy and it was launched out by the Howling. So there is a transform, all right, or the transforming from the generator to free space by the Howling. So that's why it is called a transducer here. And the transducer, that means for anything that if there is the energy transformation, that means there's going to be some power loss, all right, or energy loss. Because when we transform the energy from one condition to another, that means there's going to be some consumption or some loss. And this is due to, for the antennas, this is due to two conditions. The first condition is heat, all right? So for the energy flows in one conditioner or in one condition, there it's going to be associated with the heat dissipation, all right? And the second thing is, for antennas, there is one very important parameters that we need to take care, is that it has impedance, all right? So for any connections between two electronic or electromagnetic components, it also needed to achieve the impedance matching, all right, or phase matching. So if actually it is very difficult or it is impossible to achieve a perfect matching between two components or between two the electromagnetic devices. So whereas they're going to generate, if phase is not matched or the impedance is not matched, they're going to be reflection, all right? So this can affect the efficiency of the antennas, and so for extra antennas, efficiency is going to be 50 to 70% in this range. So it cannot convert all energy generated by the generator. And if you touch that antenna and it operates over a long time, it's gonna feel it is becoming hotter, all right? So it become hot sometimes. So now another thing we needed to take attention is that if we have two identical antennas, so identical antennas, when it operates at the transmitter side, it's gonna have the same radiation pattern, all right, or antenna pattern, with that when it operates at the receiver side. So that means if I confirms that the antenna is gain or is being pattern is fixed or is measured by the producer or the manufacturer, then we can use the edge at the transmitter side and also can be used at the receiver side, and it can offer the same antenna pattern and the same gain and the same impedance, and all the parameters should be identical. So that means the antennas has one law, is this reciprocal law. So for the reciprocal law, that means the antennas, the same antennas can be used at both the transmitter and receiver sides, and it can offer the same properties for the electromagnetic waves propagation or detection or collection or the launching out, something like that. And so mostly it is offers the pattern, all right? And when we design the antennas, the most important thing that we need to know or we are concentrated on is the antenna pattern or the antenna radiation pattern. And we can also use it as antenna pattern or radiation pattern. It doesn't matter. The most important thing is the pattern, right? So it can be antenna pattern. Or radiation pattern. So it can be characterized by the normalized radiation intensity, all right? So, and we're later gonna introduce that one, and it can be characterized by a parameter. So, there is another reference, right? When we wanted to characterize the antenna patterns, we usually take it as with respect to a reference, right? And the reference pattern is generated by the isotropic antenna, right? For isotropic antenna, that means it radiates equally in all the directions. So like a point source, all right? Like that. So we take it as the isotropic antenna because we regard the isotropic antenna gain as equals 1, all right? In the linear scale and 0 in the decibel scale. And all our other calculations or all our other the characterizations of the antenna gains or the antenna patterns with respect to the isotropic antenna. So it works as reference. So, and we need to take this that we see that the antennas follows the reciprocal law, but there are some exceptions. So the exceptions are such like it is based on the exception. Two kinds. The first kind is the antenna based on the solid state. Antenna, non-linear. If it works in linear, it also follows the reciprocal law, but if it follows the non-linear solid state antenna, then it cannot follow that one, so it is exception. Another kind is the ferrite effect. It follows the ferrite effect. So these two kinds of antennas, they do not follow the reciprocal law, and also these two kinds of antennas are not commonly used, all right, in our researches. And for example, for our mostly used, for our mostly applied projects, we usually want to achieve the very high antenna gains and the very narrow beam widths, especially at high frequency regions. So we will usually use the antennas with very large apertures, such like the cluster ring antennas that mostly used, and also the phase controlling arrays or the antenna arrays. So this is the reciprocal laws, and also as demonstrations in our analysis. Another thing is we wanted to introduce is that if the even though the antennas it follows the reciprocal laws, it also needed to make sure that there is polarization matching, all right? So that means our transmitter side, it generates with one polarization and it should be collected by the antenna at the receiving side with the same polarization, all right? Especially for the long distances or short distances. Of course, for long distances or a very long distance propagation, as polarization going to be discharged, and there are some cross polarization components, which we think it can also be helpful for the detections, especially for the radar remote sensing systems, and that's what we want to introduce. That's I usually introduce in my another course. Okay, and I will not more concentrated on the polarization in this course because this is not our focusing point. So for radiation for the antennas, there are several kinds. All right, so mostly we can divide it to be two kinds. The first kind is the conductive antenna, or it is based on the conductive current. Another kind is called the depends on electric fields. So the conductive current, that means there are time varying current flows in the antenna, and as we all know that the time varying current, it's gonna radiate the electromagnetic waves. All right, so the most typical conductive antenna based on conductive current is the dipole. All right, so this is the thin dipole antenna. So the current flows inside of it, and it can generate the electromagnetic waves. And also another kind is the biconical dipole. And also the third kind is we connect them together, let it to be loop. All right, so this is based on conductive and current. So for the electric field, it is the same. It operates at a different conditions, right? Because it's like this one. Okay. So that's because it operates, but it also has the time varying current on the surface of the antenna, but it is lumped out due to the aperture. So, all right, so this is based on the electric field mechanism. So these are two kinds of the antennas, and also for the classification of antennas. So mostly we are more concentrated on this condition. All right, especially for the radar radar, it's mostly based on this sign and this kind of conditions. And also for the antenna arrays, we just composed or poached many the identical antennas together, and by controlling its magnitude and its phase to achieve the final control of to get the beam with a much higher directivity and much higher beam gain. All right, and also the switching or the beam forming for that. So this is for the antenna arrays. Okay. So as we mentioned that for any source, it generated if it is if the antenna gain is not very high, that all of the electromagnetic waves, it has scattering angle. All right. So for the scattering angle, we usually take it as wavefront as spheres, or not the whole spheres, but spheres like that one. All right. That one. Spheres. All right. So we usually take it as spherical wave. But when it propagates into the free space, it becomes, its radius becomes much larger and larger and larger and larger, and finally it becomes flat, right? So it becomes a plane wave. So for plane waves, it helps us to simplify our calculations or our conductions for the electromagnetic waves or the Maxwell's equations, right? If we take it to be the plane waves, it becomes much more simpler and for our calculations, and actually for the detection of the weather or the radar remote sensing, the distance between the target and the radar system is very far away, so we can always take the electromagnetic waves to be a plane wave, and for the analysis. So we needed to know that how we can classify that, what kind of condition is that it is a spherical wave, that EM wave can be spherical, and at what kind of condition it can be plane waves. So there is a definition for that. I want to introduce. It is the far-field distance. So far-field distance. So that means this distance determines that the maximum error between the face of the spherical wave, the error between the face of the spherical wave radiated by the antenna and the face of the plane wave approximation. Is pi over 8. So when the maximum is smaller than pi over 8, so that means we can regard this spherical wave to be a plane wave. And finally, we can get an expression to define the distance between that. Is when the transmitter and the receiver side, the distance between them is larger than 2d squared or lambda, then we think that follows the far-field distance, and the electromagnetic wave can be regarded as plane wave. So here R is the distance between the transmitter and receiver, or the distance between the antenna and the target. So distance between transmitter and the receiver, and D is the linear aperture of the antenna. So that means the far-field distance can be defined by the wavelength of the electromagnetic waves. All right. So for much higher carrier frequency with shorter wavelengths, that means its far-field distance becomes much smaller, right? So that means even we think, oh, it's a very short distance, but it still becomes very far-field distance. And it also depends on the linear aperture of the antenna. So if you use a lot of antennas, that means its far-field distance should be also increased. And So let's take an example as when we take the 100 gigahertz as an example. So 100 gigahertz means its wavelength is around 3 millimeters. All right. So if we use the antenna, the typical Hawaiian antenna, its linear diameter is around 1 centimeter, so it's 10 millimeters. So we take it into this equation, and it's 10 square divided by 3 millimeter. So it is around 66.6 millimeter. So that means for the 100 gigahertz with the Hawaiian antenna, a typical, I think it's WR3, 3.4. So as far away distance, if the transmitter receiver side is larger than 6.6 centimeter, so it operates in the far field region, and we can take the electromagnetic waves to be plane wave. That's why in our analysis, so we just take it as the far field region here. Actually, there are many researches now. They are more concentrated on the near field. All right. For the near field detection, for very sensitive detections, such as for the materials or for much more particles, such as the roughness or materials or the atoms, detections on that based on the near field detection. And also, therefore, wireless communications. There are also near field wireless communications, because in the near field we can achieve a much more efficient controlling on the electromagnetic waves. And when it looks up into the far field conditions, then we can achieve the final propagation of the electromagnetic waves. So the near field condition is now very popular for our researchers, right? And it can give us a new visibility of visions on our physical world. So this is, but for the radar systems, we are more concentrated on the far field. So this is the condition here, and next is I would want to introduce several kinds of the antennas. So the first one that I want to introduce is the horizontal dipole. So for horizontal dipole, that means it can be regarded as a very short linear antenna. Short and linear antenna. So how? That means its length L is much smaller than the wavelength. So we can regard it as a horizontal dipole, and to characterize the edge, so that means for the horizontal dipole antennas, the radiation, it is caused by the conductive current, all right, as the radiation of the electromagnetic waves is caused by the conductive currents. So the conductive current is really the time varying current. All right, it can be expressed as IT equals the magnitude I naught times cosine. It's very simple condition, okay? And it's like this one. And I naught is the amplitude, and the omega is the angular frequency. So if we wanted to get I think for undergraduate courses, the electromagnetic field or the electromagnetic waves, most of you are very familiar with the electric field generated by a line current, all right? It can generate the electric field, all right? So for this condition also the same thing, and if we put it in a spherical coordinate system, the electric field can be expressed as like if its length is infinite, so there is current, all right, the electric field. For this one also it follows the azimuth direction of the azimuth direction theta, and this expression I node here, K, it node the intrinsic impedance divided by 4 pi, and here bracket inside is the distance, and the E minus J. K as the wave number, right? And also the propagation constant can be for a plane wave. And finally, times sin theta. So this is for the electric field. And for the magnetic field, it can be follows the azimuth direction and divided by the intrinsic impedance by theta. So this is the expressions for the electric field and magnetic field. So if you forget that, then just take a short review on your undergraduate course. So here we mentioned that there are several parameters. The first one is R, right? So that's we need to consider as the range or the distance of the propagation. The second thing is theta, is the zenith angle, and the third one is phi. This one is sorry, this is zenith angle. This is a zenith angle. So that means we needed to calculate or to analyze the electromagnetic waves in a spherical coordinate system. So we take it in a Cartesian coordinate system. So first in Cartesian coordinate system, x, y, and z. So spherical coordinate system in the pocket spherical here, sphere inside of H. So if we take one point on the surface, maybe that point is here, okay, and this is the origin, and this point, so as shadow on the surface on the x or y plane. It's like this one, right? So this angle is the zenith angle, and this angle is the zenith angle. Theta is zenith angle. Or we can call it elevation angle. This this is the thing with angle. So from here, if the source is at the origin, for example, that means the current or the not current, the power density of the pointing vector gonna propagate along which direction? Pointing vector can be expressed as half of the real part of the electric field cross product magnetic field. So we're gonna follow the radial direction, alright? We're gonna follow the radial direction times magnitude of it. Okay. So now let's take a short break and we're gonna come back after 5 minutes. Okay. 好，我们下个休息。 is along the radial direction, that means the Poynting vector or the power density depends on the distance, or on the elevation angle or the zenith angle. So zenith angle. So how to express it now? I would want to show you the details, and I hope you can. If you forget that, just take it as your homework to check how to conduct the expressions for it. And it can be expressed as beta node t square times I node square L square divided by 32 pi square R square times sin theta square. So this is the power density of the electromagnetic waves generated by the Hertzian dipole. And so now we wanted to, as we mentioned previously, we said that there should be the antenna pattern should be characterized by one parameter. So there is parameters called the normalized radiation intensity, so it can be expressed as f theta. It equals the power density plus theta phi divided by the maximum of that. So for this one, the maximum of that equals how much? Equals this constant, alright? So this is the maximum. So that means this equation finally equals sin theta squared. So this is the normalized radiation intensity, and we used this parameter to characterize the radiation pattern of the antennas. And so if we wanted to see it here now, f theta equals sin theta squared. F theta equals sin theta squared. So that means it achieves the maximum when theta equals 90 degrees. Alright? So this is the maximum, and we call this side as the broadside direction. So that means along this direction, the antenna can achieve the maximum antenna gain. Alright? So we already take it, put this side to face the target. And also if it equals, the theta equals 0 degree or 180 degree, so it equals 0. So there's no power radiation, alright, or no intensity radiation. So if we take it as a Cartesian coordinate system, two-dimensional, okay. So here this side is the y-axis, and this side is the theta axis. Theta. So the zenith angle here is theta, right? So when theta equals 0 as 1, when theta equals 90 degree as 0, so it becomes like this, alright? And this side the same thing. Right. This one. Am I correct? So now if we take it, we come back to this integration. So if we take the x or y plane, take the x or y plane for an example. So that means x or y plane, that means the theta equals 90 degree always, alright? So the f theta always equals 1. So if we take the x or y plane as an example, it always 1 over the, so in this plane, the angle is the azimuth angle, alright? So it is always plane like this one, a circle. So because this is it, this is phi, alright? So this is 1, this is 1, and this is 1. So if in the three-dimensional condition, you put them, combine them together, it's gonna become a donut shape, right? The donut, the circles like a tire, alright? So this is what it looks like for the Hertz dipole antennas. It's radiation pattern. So that means along the x or y plane, it radiates equally for all the directions, or along all these directions, right? So that means S antenna gain comes to very high, and so if we wanted to know how antenna gain is, or to characterize antenna gain. As previously we know that we use this equation to characterize the radiation pattern of the antennas. Another very important antenna is the antenna gain. So how to characterize it? And we gonna come back and see this plot. So okay, and I erase these things away. So I would reuse the spherical coordinate system again for the analysis. So this plot, it is very important because I want to use it to make it to be more easier for you to understand it. Now we take that there are, for the power density, if we want to convert it to be the power. So for power density, S, if we want to get the power, the radiated power, it should be divided by, or not, it should be multiplied by what? Area, alright? So that means if our source is at an original point, so we take integration all over this sphere, and we can get the radiated power by this antenna, the total radiated power by it. So now we take integration. So we need to, of course, S is always follow the radial direction, and A is also along the its normal direction, also follow the radial direction. So it becomes S times A. So the radiated power equals the power density times the area, the tiny area component. We take the integration over that, then we get the total one. All right. So now first we need to choose this part. So we take a small area on this part. So the first part is here, and the second part is here. So this is small part, and also along the zenith angle region. So we take this small area as it, right? So the first thing is, if this is d theta, right? So d theta is here. So this small side is d theta, and this small side is d phi. So the dA can be expressed as r d theta times r sin theta d phi. Alright, so it becomes r squared sin theta d theta d phi. So the radiated power can be expressed as another one. It is called the radiated power equals S times R squared sin theta d theta d phi. It's like this one. And another thing is we needed to consider is that we have another parameter we already used is solid angle, all right? So for solid angle, it can be expressed as d omega. It equals dA divided by r squared. So it equals sin theta d theta d phi. All right. So if you take it over the whole sphere, closed integration, it can be expressed. The solid angle for a sphere is equals how much? Could you remember? 4 pi. All right. So this is the for a solid angle, and this is going to be used in our later analysis. But here we wanted to conduct the integration for this project. So as we mentioned previously, as here, the power flow here. The power flow I have erased it. So the power density S can be expressed as maximum times sin theta. All right, times sin theta squared. And it can be expressed as S maximum times F theta, all right? The normalized radiation intensity, all right, as we definition previously. So we put it inside of it, that means S maximum times F theta. Oh, also it depends on phi, so we take theta phi, and R squared sin theta d theta d phi. So the integration of PRAD equals the integration of the whole sphere, all right, as max F theta phi R squared sin theta d theta d phi. So now let's look back to this expression. We can see that the S max is determined by the parameters of the current of the antenna, right? Is initial current, is length, and R squared as the distance between them. So they can be regarded as constant. So they can extract out from the integration. All right. So let's rewrite this expression as so here. So okay, and it's the A to the power equals S max times R squared integration of that one times F theta phi sin theta d theta. This is the integration here, and also we can express as we mentioned for the solid angle. Like this one. Okay, and now we put the subscript is RAD. So that means it is called the total radiated power. Total radiated power. So the total radiated power, that means the power launched out from the antenna aperture. Okay, power launched out from the antenna aperture. So some guys may have want to know then what is we have another kind of parameter that is called transmitted power. Alright, we usually put it as this one. The transmitted power equals the radiated power plus power loss. They have some kind of relationship. So that means if we come back to our previous investigations or our presentations on this one, the generated power here is the transmitted power here. And the radiated power is here, the radiated power. So that means during this process, there are some power loss here due to the propagation of it. So that's why we define the antenna efficiency. We call it psi. It equals the radiated power divided by the transmitted power. Okay, so now let's come back to the radiated power. Now, so the radiated power is mostly depends on integration. Alright, so here the most important is this one. So we call it the normalized radiated intensity. Alright, so it can also relate it to the antenna pattern. So for antenna pattern, as we all know that we usually put it expressed in a polar system or in a Cassegrain system, alright? So if we put it in a Cassegrain system and the Cartesian coordinate system, and it can be expressed as, for example, here, it is usually expressed as angle, alright? And here is the maybe it's the gain. Or the S21 as parameter, right? Or power. Anyway, but it looks like this one, right? This one should be a little bit higher, right? So sometimes we really use the sync function, right, to express the radiation pattern of a typical antenna. Actually, it's not exactly a sync function, but just a little bit closing to that one. But anyway, if we get this one, it can be characterized by the f theta phi. So this is the parameter related to it. Yeah. And Also, we express the normalized intensity, radiated intensity f theta phi in linear scale right here, and we also wanted to express it in the logarithmic scale or the decibel scale, right? So it can be expressed as f in dB, right? So because it equals in sin theta square, so that means it is normalized. So the maximum of it in the linear scale is 1, so the maximum of it in the decibel scale is 0, alright? So we already used that one. The normalized beam pattern, the maximum, the peak is at 0 dB here. And also another thing that we wanted to introduce to you guys is for the beam, we know as direction, also the characterization by a function, the beam pattern or the antenna pattern, and we also want to know the beam dimension. All right. So the third parameter important for us is the beam dimension. So for beam dimension, we have two kinds of parameters. The first one is the half power beam width. Beam width. And the null beam width. Beam width. Okay? The half power beam width, that means we characterize it by half power of the beam pattern, right? So half power, that means when the power of a beam, it reduced to half of that in the decibel scale. How much it can be reduced? So half corresponds to 3 dB. All right. So that means when S power reduced to 3 dB of the original point, the maximum point, so 3 dB here, this corresponds to minus 3 dB, corresponds to 2 angles, right? This side is theta 1, this side is theta 2. So the half power beam width equals so the half power beam width means it equals theta 2 minus theta 1. So this is the half power beam width. And also it can be characterized by a parameter as theta to characterize the half power beam width. And for the null beam width, for null, so what kind of condition is called null? So here is null. Here is null, the value. Okay, so this is, for example, alpha 1, alpha 2. So null beam width is alpha 2 minus alpha 1, and this can be expressed as beta null here. So this we most usually use the half power beam width to characterize the beam dimension of it, right? So for example, when you try to buy an antenna, so you need to know, first thing is you want to say its dimension, right? So its operating frequency range corresponds to its dimension. And another important is, the second important parameter is antenna gain, right? And the third important is the beam width. The beam width is related to its antenna gain because for the wavelength is fixed. The narrower the beam width is, and the higher the antenna gain is. All right. So here, this is this one. Another thing that we want to know is, for the applications, we want our beam is much more concentrated. Actually, if we look at this beam pattern here, we can see there are 1 part, 2 part, 3 part, 4 part, and 5 part. And actually, there are so many other parts. All right, it's the left side and on the right side. What we want to know is we just want to know this part, right? We want to use this part, so we call it as the main lobe. And all this, the other peaks, we call it side lobes. Side lobes. And what we want to know is, what we want to get is, we want to suppress the side lobes and increase the main lobes. All right? So we wanted to keep the ratio between both is as much larger as possible to improve the performance of the antenna. So this is the main lobes and the side lobes. Okay, now we would want to more concentrated on the main lobes here. So for the main lobes, we have a parameter to characterize it as the antenna directivity. So for this one is we wanted to further extend it to the antenna gain. So first we just connected from the directivity. So the directivity is determined by the pattern of the normalized power density theta and phi. So it is expressed as, at this condition for the horizontal dipole, it is expressed as sin theta squares, the horizontal dipole. But actually for other dipole antennas, they cannot be expressed by this one. It has their own characterizations for that one. But here, for the directivity, come back to the most important part is directivity use D to represent it. So it can be expressed as the maximum of the normalized radiation intensity divided by the average of the normalized radiation intensity. So the maximum of it, because it's normalized, the maximum is 1, all right? And the average, that means we need to take an integration of h over the whole solid angle, all right? Or define the omega, all right? So this is 4 pi. Because it is average, so it is divided by 4 pi. Yeah. So this is the expression for the directivity. More general condition like it, and then let's take it further. Is what we wanted to get. So could you remember what this can be expressed? So actually, if f theta phi equals 1, the integration of this one can be expressed as how much? 4 pi, all right? When f equals 1, always. But if it is not equal 1, so it also has a solid angle, just like omega p, if f is not equal to 1, because it has its own radiation coverage area, all right? So we call it omega p. So the omega p can be expressed as 4 pi f theta phi sin theta d theta d phi. Here, just name this parameter here. So this one can be expressed further as the expression expressions by it equals 4 pi or omega here. So now I would want to further to do that as it can also be expressed as another condition as so the averaged normalized radiation intensity, it can be expressed as the radiation of it for let's come back to the this part. So if I time these both terms on both sides of it, so times S, let me change the color, separate, S max times R squared, S max times R squared, okay, on both sides of it. So that means it's 4 pi R squared, S max. Here is S max R squared, F theta phi sin theta d theta d phi. Okay, now we know this one is the radiated power. All right, this one is 4 pi R squared S max. So now let's do it further. Is that the maximum power density divided by this one, and also if we put this side to be the S max divided by RAD divided by 4 pi R squared. So that means the maximum power density divided by the average power density. This one. So it can also be expressed by the power, by the normalized radiation intensity, and also by the power density also. These two kinds. Oh, okay. And just to take care of it, is because we wanted to express it, and we're going to employ it in our later analysis by it. So sometimes you're going to say, okay, that's so difficult, all right? Because we get the, if we wanted to get the solid angle, we need to take an integration of it by this equation, all right? Sometimes we think we wanted to simplify it. So, for example, we come back to this one. So, if the beam is covered by this small region, okay, it's the coverage, like this side. So on the x-axis, is characterized by the beta x, and on the y-axis or along, and it is expressed as the beta y. So the omega here can be simplified to multiply beta x plus beta y. So, for example, if we know our antenna, it usually give us the its beam angle is at the vertical polarization and at the horizontal polarization. So we can multiply both together to get the solid angle like that. This is just a method to simplify your calculation, okay? By just to simplify the expression by this one. So you do not need to do the integration because it can sometimes can be very, very difficult to get that. So now we get the directivity of the antenna gains. Now what we wanted to show as the antenna gain. So for antenna gain, as we mentioned, or we usually used is, it can be expressed as G. Alright? So here we see that the directivity is expressed as by this equation. Right? So what we wanted to know is the antenna gain. It should equals the 4 pi r square as max, 4 pi r square as max. Directivity is divided by the radiated power here. And for the antenna gain, is divided by the transmitted power. So as we know that the transmitted power equals the radiated power times plus the power loss, alright? So it also has another condition that is expression by this equation here. So this one is eta is the antenna efficiency. So that means if the efficiency can be 100%, that means there is no power loss. Alright? Actually, it's only 50 to 70% as we mentioned previously. So that means we have power loss. And now we can express it as pi r square as max divided by radiated power. So this one divided by PT equals antenna efficiency, alright? Psi times this part is the directivity. So that means the antenna gain can be expressed by the directivity below this equation. So sometimes some guys they wanted to calculate the antenna gain by the beam width or by the directivity. Actually, we need to know that the directivity is not equal to the antenna gain. It should be multiplied by the antenna efficiency here. So if it is 50%, that means it has a 3 dB reduction, alright, with respect to the directivity of the antennas. Okay, this is the expressions for the antennas characterizations. And another thing that we wanted to introduce is the aperture. All right, another thing is aperture. So for the Hall antennas, we have the it has physical apertures, right? For example, for Hall antenna, let's let me take a diamond Hall antenna as an example. So it has the physical aperture size here. This is its physical aperture, right? We use AP to represent it, physical aperture. But sometimes we do not have the physical aperture. For example, we have the dipole antennas, as we mentioned previously. So it has no aperture, physical aperture, right? It's not the arch for all of them, the free space. So we need to define another parameter, AE. We call it effective aperture. So even there are some devices that do not have the physical apertures, we can define it as the effective apertures for the characterization of it. So now what we wanted to do is I wanted to go back to take the short review as we mentioned previous slide as our definition for the solid angle. Okay, the solid angle is divided by this equation, right? So d omega equals dA divided by r squared. So that means if S coverage is if the plane is a flat plane, we can use omega equals A divided by r squared. So here, for the actual arrays divided by this area, for example, the aperture as an example is omega p, the solid angle, can be expressed as the it can be related to the A here, and so let's come back. Yes, integration of it. Integration of it and A. So, or r squared. Integration. So after integration, we have another expressions for it is we can get the final directivity d. It can be expressed as the 4 pi lambda squared divided by AE here. So if we get the antenna again, it equals 4 pi lambda squared and psi times AE here. So psi is related to the efficiency, and AE is the effective aperture here. So if we know the aperture of a whole antenna here, so we can calculate the antenna gain, just an estimation on it based on this equation. But actually it not always works because we need to know the exact values of the efficiency, antenna efficiency, and its effective aperture. For the whole antennas, the effective apertures and the physical apertures, they are roughly equal to each other, but for the dipole antennas, for example, it is difficult for us to extract the effective aperture here. So we need to find some method to characterize it. And finally, actually, the effective aperture with the physical aperture, there is another parameter. It is called the aperture efficiency. So it is expressions for it, like this one. And so this is the antennas for it. And from the antennas, we needed to further, if we have two antennas and there is electromagnetic propagation between both, what we wanted to obtain it as we want to characterize the propagation of the electromagnetic waves inside of it. So what we wanted to do is we got together an expression for the power loss between the transmission from the transmitter to the receiver, and we're going to introduce that after a short break. Okay? start on the conduction of the first transmission formula. The first transmission formula, it can usually it is a simple expression, all right, because it is conducted by using the MATLAB. It has a function on it, and here we just wanted to know how to conduct it. And so first, let's start by treating our transmitter antenna as an isotropic or lossless antenna. Isotropic lossless antenna. That's treated as an assumption. So as power density equals how much? Isotropic, that means it covers by sphere, right? And the transmitted power divided by H. So this is on the transmitter side. And on the receiver side, what we wanted to get as the received power density SR can be expressed as it equals the transmitted power density isotropic. Actually, it has antenna gain, so it can be expressed by this equation, and it can be further expressed as cosine p dt. All right, the directivity times isotropic, like this one, and can be expressed as cosine t dt pt divided by 4 pi r squared. So this is the expressions for the on the transmitter side and the receiver power here. So as we know that the dt, the directivity, can be simplified as 4 pi pt divided by lambda squared. So this equation can be expressed as cosine t at pt divided by lambda square r squared. So this is the received power. This is just the power density, right? So if on the receiver side intersected, we call it intersecting power. This should equals the power density times the area of the aperture, right? Area of the aperture. Yeah. So it equals cosine t at pt divided by lambda square and r square. Here. And further, we needed to know is the integration of the received power. So this is just the intersected power. The intersected power, that means the power collected by the here is the intersected power collected by the aperture. But if it becomes the received power, there is also a transfer between this, determined by an efficiency of the antenna at the receiver side. We call it psi r. So that means when we come back to here, the received power equals cosine r times intercepted power. So it equals cosine t, cosine r, at, ar, pt, the transmitted power, divided by lambda square and r square. So that we wanted to get the power loss of the phase formula. It is related to the received power and the transmitted power here. So it can be expressed by the formula as the expressions as the received power divided by the transmitted power can be cosine t, cosine r, at, ar, lambda square, and r square. So this one. And so the received power divided by the transmitted power expressed as a free space path loss, like this one, right? The ratio between both. So that means the free space path loss can be expressed as lambda square r square divided by cosine t, cosine r, at, ar. Can also be expressed as what? It can also be expressed as 4 pi r over lambda square times 1 over gt over r gr. So times this one. So now we get the expressions for the power loss. It can be expressed as only like 4 pi r lambda square 1 over gt 1 over gr. So in the logarithmic calculations, actually the gt is the function of theta and phi, and the gr also the function of theta and phi. Alright, so we can get the free space path loss in the decimal scale. It can be 10 times log 10 4 pi r over lambda square minus dt minus dr dB. Alright, so this is this one. Actually, sometimes, mostly, we regard gt equals 1 and gr equals 1. So there's no antenna gain. The free space path loss can be expressed as 10 log 10 4 pi r over lambda square, and sometimes we can look at it as 10 log 10 r distance plus 10 log 10 f frequency plus a constant, right? So if you check the mostly equations for the free space path loss, you can get this equation, such as an expression. Actually, it is obtained by this equation here, this one. So this is more formal equations because it combines. It considers the antenna gains from the transmitter side and then the receiver side, and so these things we cannot forget it. So this is for a point-to-point antenna gain. And another thing is, so this is just for the condition that we have antenna at the transmitter side and antenna at the receiver side, and we have the electromagnetic waves propagates from the transmitter to the receiver here. All right. So another thing is for the radar systems. we have a reflection, right? So this is the transmitter, this is the receiver, and the distance from the transmitter to the surface is R1, from the receiver to the surface is R2, for example. And the reflection here, there's no reflection loss, okay? The reflection loss equals 0, so that means there's no path loss due to the reflection. So it's just a spectral reflection or mirror reflection. So our path loss here is expressed by this equation, all right? So I'm going to express it as, okay, this one. So the path loss here equals R lambda square 1 over dt dr. So now for this part, free space path loss 1 is R1. Free space path loss 2 is 4 pi R2 lambda square 1 over dt and 1 over dr. So the total path loss is this correct? Can I calculate it by this equation? This formula for the total path loss? Is it correct? So it's not, right? We cannot add the path loss by this part and the path loss by this part together, because the path loss is not in a linear relationship with the distance, all right? So we can say the path loss and the distance is a square law, not a linear relationship. So what we should do is it equals 4 pi R1 plus R2 square over lambda square 1 over dt dr should be expressed by this equation. We should add them together to calculate the path loss. If there is a reflection loss here, then you can add reflection loss here. Add one loss if it is not 0, but actually here for simplification we set it to be 0 here. So now that's what I wanted to introduce you guys all for this lecture. And for next week, I want to introduce the antenna arrays. So we have multiple antennas and how the electric field can be the total or the final electric field that we can obtain when several antennas work together. By controlling its magnitude and by controlling its phase. All right, these are both very important parameters for the antenna arrays. So okay, now I think this lecture is done, and I'm gonna see you guys next week. Okay.